Now again I have reloaded everything, so let's get to the next issue. I'm rebooting the system, starting the not my fault. This time it is stack trash or stack corruption. I'm going to crash the system, assuming that it is a stack corruption. Before we jump into the debugging, let me give you a warning. So I have no clue how they have implemented the stack corruption. Based on how bad the stack is corrupted, we may or may not be able to get anything out of this particular issue. If we are able to point to the binary somehow, which is not my fault, driver, we are more than achieved. So a stack corruption is a pretty complicated issue even in simple scenarios. So the single most important information, which is stack or the call stack, is corrupted. So we don't have it. That is one thing I would like to mention here is some way or the other, if you are able to point the issue correctly to not my fault driver, we are good to go. Our analysis more than complete. So being said that, let's get back. Crash happened and we are going with bang analyze FMV. I'm not expecting bang analyze FMV to give anything, but if it is giving something good, let's see that. This is the output of bang analyze FMV. It is not finding any binary at all. As you can see here, the EIP is pointing to null. The instruction pointer is completely corrupted. The ESP look okay to me, but we need to verify that. And it is not pointing to any binary or any particular information it is able to obtain. K-mode exception not handled. The crash happened in IRQL passive level. That's why we are getting C000005. It is an access violation. Usually the exception address pinpoints the driver function that caused the problem, always not this address, as well as the date of the driver image, blah, blah, blah. So not very useful. Let's see what we can find. One of the things we can see here is the process name. It is giving us the correct process name, not my fault.exe, but in this case, there is a driver associated with it, but normally the process is just a scapegoat. When it comes to kernel drivers, proper kernel drivers doesn't have any association with any process. Most of them are process agnostic. So they don't care which process context it's running onto. Although you are seeing not my fault, that's not a good pointer. We need to do better than that. One of the things we can see from here is that bang analyze FMV, unlike in the previous case, is not giving us any good information. So it's not really helping and we need to do more work than bang analyze FMV. Going with the dot trap, again, it's not going to be of much help because all the registers are corrupted. Now what is next? If you remember any stack corruption we were dealing with, what we used to do? We used to find the stack base and stack limit. Then we do a raw stack dump using the DPS command, and we'll see if any of the registers are valid, like EIP, EBP, or ESP. If any of them are valid, we use them to limit our search. But in this case, EIP is not valid. ESP, we are yet to verify. And if possible, rebuild the stack using the K command equal to parameters. So that is what we're gonna try to do here. And if things works, we may get a stack. If things doesn't work, we may not get anything. At least we're gonna try something. You can try with the stack command. So stack command, executing the stack command is one of the procedures of bang analyze FMV. If you want, you can try, but I don't think it's in this case giving you any more information. This is a stack command which is getting executed. The next command we would like to type here is bang thread. Bang thread will give us the kernel mode stack base and stack limit. That is what we need to find out right now. The kernel mode stack base and stack limit. As you can see here, the base and limit. The base and limit right here, that is a stack base and stack limit in the kernel mode. Just like in the bang tab. What we're going to do? We're going to do a DPS based on that. DPS, if you remember, dump pointer with symbols. If you have any confusion on this particular command or anything we are doing, just refer back to the the presentations, the previous presentations, so I'm not going into any details here. DPS, then the start address and the end address. The good thing is that the kernel mode stack is very small compared to user mode. It should print pretty less number of entries. Looking at the ESP right here, so we can see the ESP is looking valid because it is very close to the stack base. If you look clearly, ESP looks to be valid, which is a good thing. How do I know ESP is valid? The general value of ESP should be between the base and limit, which is what is seen here. So ESP is the value which is highlighted on the screen right now, and the base and limit is in the bottom in the DPS command. This base and limit right here is covering this ESP, and ESP is in fact very close to the base. Looks like EBP is not valid. It is null. EIP is also null, so it's not valid. EBP and EIP is invalid, while ESP looks to be valid. Another thing to notice here is the IRP on the stack. There is an IRP pending on this particular stack. You can do a bang IRP on this to see if there is anything interesting on that IRP, because anyway you don't have your stack. Your valid stack is missing. You can go with the IRP. I'll tell you what are the other things you can do in the case of a stack corruption other than the stuffs we are trying to do right here. I'm pulling up a scratch pad right here to collect a valid stack pointer, instruction pointer and stuff like that. I executed the DPS command. DPS command is in progress. ESP looks to be valid, that's why I put it in the scratch pad. Now I need a valid EIP and ESP. What is the use of those three things? To build stack using K command, the arguments to the K command. DPS is complete. I'm looking for patterns on the stack. As you can see here, not my fault is not anywhere on the stack at all. Not even a sign of not my fault binary on the crashing stack, even in the raw stack dump, which is unfortunate. Which means that we are not able to find our culprit so far. Now, what I'm going to do is I'm going to limit my stack dumping with the ESP, assuming that the ESP is valid. I'm going to start from the ESP till the base. Looking at anything interesting, any drivers, any interesting drivers. There is an IO call driver. IO call driver and an IRP pending on a stack. If you're into driver programming, that is a definite lookout for you. But if you don't know what that means, probably that's a different thing altogether. IO call driver is how you transfer your IRP to the next driver. Don't worry about it right now, just putting out there. So when you have a difficult situation like this, you need to look for other clues. You're expanding your clues. This IO call driver on the stack could be, if you can find out a corresponding IRP, could be a useful thing. Probably it's just nothing, but something to research forward. That's my point. Right now, I'm not going to do anything with that IO call driver. Right now, only thing I'm going to do with that IO call driver is I'm going to take it as a value for my EIP. As you can see, my EIP is 0. Anything better than 0. And I would prefer to have a valid binary address, which is in this case IO call driver and within the stack. So I'm going to select that address as my EIP. I'm going to put that in the scratch pad. Probably I'm completely wrong. This is all hunches and guesses. It's not exact science because the stack is corrupted. The value on the top of that looks to me like a valid EBP because that is very close to the stack pointer. And if 82250C8 is a return address like I was assuming, definitely BDD0FDE4 could be a valid saved EBP. I could be completely wrong, but let's see. I'm going to select that value BDD0FDE4 as EBP. Now, what I'm going to do is I'm going to go into the documentation of the K command, like we always do. This is the documentation of the K command. So this is a format we are going to use. We have used this before. So Control V. We are going to give all these pointers right there in the position. K equal to, first is the base pointer, stack pointer, and then the instruction pointer. That's what I'm doing here. Space, then the stack pointer. All could be invalid. At least we are getting a better stack here. As you can see here, we are getting a better stack. This stack right now makes a little more sense. There is a device IO control going into the kernel, and the device IO control is going to hit a driver, IOF call driver. That is IO call driver. We are successfully able to build that particular stack. Still, we are not able to pinpoint to the correct driver, which is causing the problem. But that's okay. So this is a very good point. We didn't have anything when we started the debugging, but right now we have a valid stack. Right now, at this stage, the next thing to do is to do a bang IRP on that pending IRP, because it's a device IO control call is pending and it is to be handled by a group of driver or a particular driver. That IRP's device stack location will give us more clue about what is happening inside the kernel. I'm going to take the IRP pointer from the bang thread command, bang IRP, and then the pointer. So as you can see here, the IRP is pending on my fault. This could be a problematic driver. There is an IRP pending on a device IO control, and there is a third-party driver which is that IRP pending on. What we have done so far is we rebuilt the stack. We found out that there is a device IO control in progress, and device IO control will always have an IRP, and that IRP is pending on a particular third-party driver. It is a good place to start. So right now, if it is a production scenario, what I'll do is I will rename this particular driver and I'll see if I can reproduce this particular issue after renaming the myfault.sys. If you want, you can dig further into myfault.sys, like which company it is from and so on and so forth. What is the purpose of that driver? Why it's happening inside this problem? Is there any update for that driver? So on and so forth. But right now we are not going to do any of these things because we know all about myfault.sys.